Within the mechanics topic of constant acceleration, you may not only find SUVAT questions based in a horizontal direction, so thing moving left and right, but also moving in the vertical, up and down. That is to say that an object will be moving freely under gravity. So gravity constantly pulling it downwards, while it may initially have some upward motion or start bouncing up and down. And just at this stage, say freely under gravity means we don't have to worry about anything like air resistance. Now, because these are still SUVAT questions, we're still working with constant acceleration, we will be working with the equations from the main SUVAT video. If you haven't watched that yet, if you haven't covered the introduction to SUVAT, I would strongly advise you do that first, because it just gets you to grips with the kind of equations we're going to be using. Although all the same, I am going to just recap them now first. So the acronym SUVAT comes from the 5 characteristics we can describe something as having if it's moving at a constant acceleration. So S is standing for displacement, which is like a distance travelled in a given direction. So the specific distance between the start and the end, regardless of what path you took. U is the initial velocity, so how fast are you moving at the beginning and in what direction. V is the final velocity, how fast are you moving at the end, in what direction. A is traditionally acceleration, although because we are working under gravity, we are specifically going to be using gravity for our A value in every case. And then finally, T is time. And then just for the equations that we're going to use, we can say that V equals U plus AT, V squared equals U squared plus 2AS, S equals to a half U plus VT, S equals UT plus half AT squared. And then finally, the fifth equation that's kind of debatably its separate thing, or just an extension of equation 4, S is VT minus a half AT squared. So what we'll do in each question is just identify which at least 3 variables do we already know, what are we looking for, and which of these equations contains those variables so that we can plug the numbers in and rearrange to solve for the missing notation. Some other just phrases we want to make sure about. If we're saying that we're going from rest, that means that your U is 0, the thing is starting stationary, it has no initial velocity. Or if we're going to greatest height, so if something is then rising and falling again, at this exact point here, at the greatest height, your velocity is 0. Because if you still had a positive velocity, then you would still be moving upwards. If you had a negative velocity already, you'd be going downwards already. So in that moment, you instantaneously have 0 velocity. There is a moment when you are flat, essentially. With all that in mind then, if we just move on to an example question. So here, a stone is thrown upwards from a point 2 meters above the ground at 9 meters per second. Taking g as 10 meters per second, so here they're specifying that that's the value we should take as gravity. Usually it'll be 9.8, and that is what we're going to use in the subsequent questions, but here, saying we use 10, find the time taken for the stone to hit the ground. So, to be clear, we've got some starting point, which is 2 meters above the ground. Our particle is going to be initially projected upwards, and then it's going to fall back down to this ground. So initially going up with our speed of 9 meters per second, and gravity is 10. We want to know how long it'll take to hit the floor. Well, just writing out our acronyms, so S, U, V, A, and T. The displacement in this case, because we're starting up here at this point and ending down here, if we were to take up as positive, it's up to you whether you take up as positive or down as positive, so long as you're consistent. If we take up as positive, then our displacement is a -2, because we're ending up 2 below where we started. So S will be -2. For U, because that is going in the upward direction, we'll just take that as a +9. We have no idea what velocity it's going to hit the ground with. When something hits the ground, you cannot say it has a v of 0 because it can't hit an endpoint with a velocity of 0. It's a collision. If it had a velocity of 0, it wouldn't be moving, and if it's not moving, it can't collide. After it's hit the ground, it may come to a stop. It depends on what the situation says, but it doesn't hit the ground with 0. A, as I say, we're taking gravity as 10, but because gravity is obviously acting in a downward direction, that's against the upward direction, so acceleration is minus 10, and then t is what we're after, so we don't need v. So S, U, A, and T, the equation that involves those is equation 4, so minus 2 equals 9 times t plus half times minus 10 times t squared. Just simplifying that first of all, so minus 2 equals 9t minus 5t squared. And what we can now do is bring all this onto the same side. So minus 5t squared becomes positive, so plus 5t squared. 9t now becomes minus 9t. The minus 2 stays minus 2 because it hasn't moved. You now have a quadratic equation, and this you can solve either by factorising or using the quadratic formula. We can just put this into two brackets, so we can say it's going to be 5t and t in order to times together to make the first term of 5t squared. Now, to make 2, we're either going to have a 1 and a 2, or a 2 and a 1. In order to make minus 9 in the middle, we're going to want this to be minus 2 here and plus 1 here. And you just want to check that. So 5t times t is 5t squared. 5t times minus 2 is minus 10t. 1 times t is plus t. And then 1 times minus 2 is minus 2. So we've got the 5t squared, got the minus 2, and minus 10t plus t gives us that minus 9t there. So this is the correct factorisation. And then once you've factorised it, we can just work out what t value this is true for. Either this is t equals minus a fifth, because 5 times minus a fifth would be minus 1, and minus 1 add 1 is 0, or t equals 2, because 2 minus 2 equals 0. And remember, when we're factorising, we want to make the brackets equal 0, because they're two things times together to equal 0, so one of them must be 0 in itself. This being said, only one of these can be the true answer to this question, and that's going to be t is 2, because we can't have a negative time. And now the reason for why we have a negative answer is because, mathematically the equation doesn't know that we started up here. From the equation's point of view, this curve will keep on going down on the left, and in both directions keep on going down infinitely. Additionally, the reason why we took this less precise value of g in this case, using 10 rather than 9.8, is because it just made this subsequent factorising simpler. That's not to say that you should take 10 or g as 10 if the question doesn't specifically tell you to. Under normal circumstances, we would be using 9.8 regardless. So yeah, that's how we can go about a SUVAT under gravity question. As you would with a regular SUVAT, just identify your S, U, V, A, and T. In this case, A having to be gravity in the downward direction. It may be advisable to draw out a model of the system, just so you can see, okay, we're starting here, we're ending up below here or up here. How many times are we going up and down? What's the initial? And so forth. Yeah, once you have your equations, you're just once again plugging in the numbers, rearranging and solving as necessary. If we're okay with that, let's just see how you might get along with this next one. A ball is fired upwards at 39.2 meters per second, then moving freely under gravity, so no air resistance. Find its greatest height and how long it's been above the height of 34.3 meters for. Pause the video, have a go for yourself. Just again, think carefully about which values the question has given you. Press play again when you're ready to compare. So, we've got two stages to this question. Obviously, we're first of all trying to find the greatest height, and we're trying to find how long it's specifically above this height. So, if we start with the initial one, presumably, because they haven't specified that it's a point above the ground, we'll say, okay, it's going to be launched from the floor then, or some baseline that all of these heights are measured from. So we're just going to go up and down. Our S initially is what we're trying to find. U is the 39.2. V, because it's the greatest height means V is 0. A is going to be minus 9.8. 9.8 because they haven't specified we should use anything else, and minus because gravity is acting in a downward direction while the object is moving up. And then we don't know what T is. So because we're after our displacement, we don't really have to worry about T. So we've got S, U, V, and A. The equation involved those is question 2. So V squared equals U squared plus 2AS. So 0 squared equals 39.2 squared plus 2 times minus 9.8 times S. Okay. Well, if we just want to simplify that first, you end up here with 0 equals 1536.64 and then minus 19.6 S. Rearranging this, because we want to get S, let's make S positive. Let's add it onto the other side. So 19.6 S equals 15,000, and so 1,536.64. And to get S on its own, we'll just do a division, which gives us a value of 78.4 meters. So that's how high this ball is going to get. Now, this may be how high it's going to get. That's your first part. But the second part is then talking about a different height. How long is it above a height of 34.3? If I just clear up this space so we have a bit more to work with. Now we're going to change a couple of the parameters here. Obviously some are staying the same. We're still going to have an initial velocity of 39.2. We're still going to have an acceleration of minus 9.8. Although now we know the displacement is going to be 34.3. Whether we're going on the upward side of the arc or down again, that would be the displacement when it's like crossing this threshold. That is the height above the ground. And then because we're having to go up and then back down again, we're now looking for a model that the very least goes beyond, well, below this height again. The easiest thing to do that is just when it hits the ground again. But when it hits the ground again, we don't know what V is. And then in general, we're looking for time now because we're looking for how long. So this time, we're ignoring V. We're back to using S equals UT plus half AT squared. So 34.3 equals 39.2 T plus half times minus 9.8 times T squared. Just simplifying that bracket first of all. So 34.3 equals 39.2 T minus 4.9 T squared. Bring everything onto the left-hand side, you get 4.9 T squared minus 39.2 T plus 34.3 equals 0. Now at this point we can either use the quadratic formula because these are decimals, so plug in your A, B and C into the quadratic formula. Or in this case, if we can spot, there is a common factor we can divide through by. You can divide through by this 4.9. If you do that, you're just left with T squared minus 8T plus 7 equals 0. And this we can break down into two brackets of T minus 1 and T minus 7. From these brackets then, if we just want the values of T at which it is at 34.3 meters, you'd have T is 1 and T is 7. These are the values you would have got from the quadratic formula if you'd done it that way. The questioner is specifically asking how long is it above this height of 34.34. though. So if we know that it goes up through the threshold of 34.3 at 1 second and comes back down at 7 seconds, how long it's there for, it's above that height for 6 seconds. If we're okay with that, let's just have a go at the end at an actual exam question. So, a ball of mass 0.3 kilograms is released from rest at a point which is 2 meters above horizontal ground. The ball moves freely under gravity. After striking the ground, the ball rebounds vertically and rises to a maximum height of 1.5 meters above the ground, before falling to the ground again. The ball is modelled as a particle. Find the speed of the ball at the instant before it strikes the ground for the first time. Find the speed of the ball at the instant after it rebounds from the ground for the first time. And find the time between the instant the ball is released and the instant when it strikes the ground for the second time. So, first of all, if we just want to draw a quick sketch of the model, just to make sure that we're happy with everything that's going on. So we're starting at a certain height above the ground, which is 2 meters. It starts by dropping. So there's going to be no upward part this time. We're just going to go straight down. Then it hits the ground. Then it bounces up again, not as tall though, and then comes back down here. So this height being 1.5 meters. Now obviously the idea is because it's bouncing up and down vertically, strictly speaking it should be a straight line going back over itself. But for the sake of visualizing here, like I did in the first example, we're going to draw it going from left to right, spreading it out so we can clearly see each stage of the motion. Next thing to point out is just from the description in the question, they've told us that this ball has a mass of 0.3 kilograms. If we may notice from the SUVAT equations, mass never comes into it. This number is here just as flavour text. We don't actually need it when it comes to our working. So just say a ball is released from rest. So it's initially, from rest, it's initially starting at 0. Yep, and it has this height of 2 meters. It's going to fall freely under gravity, so we use gravity as our acceleration. There's no air resistance to change that. And then, yeah, then it talks about after it struck the ground. For the purposes of part A of the question, no, we're just after the speed of the ball and the instant before it strikes the ground for the first time. So if we construct a SUVAT for that, so S, U, V, A, and T. Once again, I'm going to take upwards as positive. Some may prefer to use down as positive in this case because the initial motion is down, otherwise in my version it's going to be all negatives, but I personally prefer to always keep upwards as positive just because it's consistent. So here then, if we're starting above the ground and then we're going to drop down to it, and it's a height of 2 meters, our displacement to when it hits the ground is -2. The U, because it's released from rest, is going to be 0. V is what we're trying to find, the speed of the ball the instant before it hits the ground, before it loses any energy to the ground and so changes. Acceleration is going to be -9.8 again, because again 9.8 because it's gravity, they haven't told us to use anything otherwise, and gravity again is going downwards, so it's negative. And we also don't know time. So S, U, V, and A, that equation is your V squared equals U squared plus 2AS. In this case, the V we're after is already more or less the subject, so we don't have to do much rearranging. We'll just need to square root afterwards. But to start with, we can say 0 squared plus 2 times -9.8 times -2. So you have V squared equals 39.2, because the minus times the minus makes a positive, and then it's just 4 times 9.8. This then leaves V being the square root of 39.2, which is approximately 6.26 meters per second. That's our answer to part A. For part B, the speed of the ball the instant after it rebounds from the ground for the first time. Now, we cannot assume that it's going to be the exact same velocity, just in the other direction. In fact, we know it isn't because the ball doesn't reach the same height. If it's reaching a lower height, it means it must be starting with a smaller velocity. And again, that's because some energy will have been lost to the ground in the impact. So, because it's a slightly different situation, we have to draw or write out a new SUVAT. just say over here, so our S, U, V, A, and T. S is now, what we're going to do is we're going to go up to the greatest height here, because it is a value that we definitely know for this second arc. So we're going to go up by 1.5. The U is what we're after. By looking at just going up to this greatest height, we can now say that V is going to be 0. So it just say the other option would have been to go back down to the ground again and said displacement was 0. Just the problem is we don't know what that V would have been either, so it would have been another unknown. This way we know it's 0 up here. A, once again, going to be minus 9.8, and we still don't know what T is. Yet again, we have an SUVA, so V squared equals U squared plus 2AS. Just this time it's the U we don't know. So 0 squared equals U squared plus 2 times minus 9.8 times 1.5. From this we just get that 0 equals U squared minus 29.4. So bring the 29.4 onto the left hand side, so it becomes positive. That just equals U squared. So U is going to equal the square root of 29.4, which gives us approximately 5.42 meters per second. So we can indeed see that the velocity with which it's then leaving the ground again, like an instant later, is already definitely less than the velocity with which it hit the ground before. For part C, find the time between the instant when the ball was released and the instant when it strikes the ground for the second time. So after the time it takes to get from here all the way down here. Now the fact that here we've had to use two different SUVAT equations shows the situation has changed, and if the situation changes partway through, we cannot consider it all in one go. We're going to have to find the time to get from here to here, and then separately the time to get from here to here. To get time 1, that's going to be from this section then, using this same SUVAT model as before, because it's still the same SOA. As ever in this kind of situation, I always advocate using the values that the question already gave you, rather than the value that you worked out yourself, just in case you got it wrong. And either way, in this case, you will have been rounding. Here, these are definitely correct and precise values. So if we use S, U, A, and T, that's S equals UT plus half AT squared. So minus 2 equals 0T plus a half times minus 9.8 times T squared. So minus 2, because 0 times T is just 0, we end up with just minus 4.9 T squared. So T squared is going to be minus 2 over minus 4.9. Now we'll keep in a simplified form of 20 over 49 because it's a long decimal. Square rooting this though, you end up with T just being approximately 0.64 if they were to go to 2 decimal places. That's your T1. For T2, we have a couple of options. We can either take this time to get to the greatest height and then double it, or we can create a new SUVAT expression where we're going from here to here again to a displacement of 0, just then using a different V value and so forth. I'm just going to use the formula that we already have up here, just because we already have those numbers. So for after this T now, so get S, V, A, and T. So we'll now use that fifth equation. S equals VT minus half AT squared. So 1.5 equals 0T minus a half times minus 9.8 times T squared. C is very similar. So 1.5, 0T is still 0. Here, minus of a half times minus 9.8 is going to be positive 4.9 T squared. So if you then just do your 1.5 divided by 4.9, that gets you a fraction of 15 over 49, which, if you square root it, gets you approximately 0.55 seconds. This is not T2 yet though. T2, as I say, would be double this because we're going at this time here, the 0.55. That's just to get from where we bounded up until the maximum point. To get the rest of the way, it's going to be that same time again because it will be a symmetrical arc because it's constant acceleration. So T2 is then going to be 1.1 seconds. Yeah, all of these being seconds. So finally, the total time is going to be these two numbers added together, which is going to get you 1.74 seconds from when it's first released to the instance when it strikes the ground for a second.